Good evening, Doctor. This is Nachamba de Mariam presenting to you an explainable dual module ensemble architecture for microfinance credit scoring under severe class imbalance, institutional domain shift. I'll go straight to the contents. This is the content of our presentation. I'll have the introduction, related work, problem statement, the research, and everything. And then the background. Basically, Uganda's Tier 4 finance sector handles over 20,000 SACCO institutions, and it's managing 3 trillion Ugandan shillings annually outside formal credit bureaus. And we looked at a portfolio at risk of 15 to 25% in Uganda versus the one of 5% globally. And that means that up to 25 Ugandan shillings per 100 is lent but may never return. We looked at one of the reasons that there is a credit bureau gap. Since Uganda is a Tier 4 institution, has Tier 4 institutions, it cannot cross-check institutional borrowing, and that means there is a silent double-dipping gap which is undetectable. The other reason, we look at the appraisal bias, where loan decisions are based on relationships, not the data. And this means that people can acquire loans and they are not credit-worthy, credit-worthy. Basically, our project deals with 2 modules. The first module is a loan application gatekeeper. And basically, in this application gatekeeper, it looks at the loans before someone acquires a loan. It acts as a predisbursement binary default predictor, and it helps to see who is worthy to access the loan. Then we also have the second module, which is the loan monitor. Basically, this loan monitor works with ongoing loans, and it looks at the to see how active these loans are, and it also gives it uses trajectory features to see what is happening to the loan. We used XGBoost as a production model, as we will see further. Then we also had Sharp, and we also had the area under precision recall curve and the group Sharp split. We had the related work. This is the literature review, basically, what was happening. We had some AI in banking, and we used the logistic regression and the linear models. And one of the architectural limitation was that since it was linear, it fails nonlinear circle interactions. And then it also requires formal credit history, which are not applicable to Uganda's Tier 4. We also looked at the effective credit risk prediction. And this is the random forest as its mode and the gradient boosting. These are the key results we got. Its F1 score was 0.82 on balanced sets, and the limitation was that there was no group split and the circle leakage was not addressed. The context limitation was that there was single institution data set, and it limited geographic generalizability. Basically, this is literature review of the related work that we did. The problem statements, we had the major problems we saw was the appraisal bias, the identity trust gap, and the blind spot. As you can see, it's as I explained earlier, that appraisal bias, someone acquires a loan, they are not worthy. Someone can acquire a loan because they are known, and they end up acquiring 5 million loan, and yet they can pay 2 million, and that leads to losses in these financial institutions. There is an identity and trust gap where someone can access a loan and they don't even have the rightful identity, or someone can acquire a loan in the names of another person. Then there is the blind spot where we cannot see early warnings for the deteriorating loans. This was the computational problem where we had a 3.1 to 1 ratio of class imbalance, the default to the non-default. Go through the research questions. The research questions included this to conduct a 24-question EDA, to design and train ML architectures, to deploy a Flask recipe, and these are the questions we came up with. Because of time, I want to go direct to the modules. This is what we had as the methodology and system architecture. Then we also had the description of the exploratory data analysis. Basically, our data set had 19,955 training eligible records from these circles across 15 districts. And these were filtered from the 20,854 raw records. These are the columns, and the target was that it will flag binary for the default, and then the defaulted was it had a portfolio at risk of 7 threshold. And I'll go straight to the module architecture. Our module architecture, we use the XGBoost. XGBoost basically uses decision trees, and it had an objective function, which is this. And here I'll explain about the decision tree. The decision tree majorly is a distilled tree which employs a greedy and the depth limited recursive binary partitioning of the feature space, and it minimizes mean squared error on blended soft labels to produce shallow and highly interpretable leaf probability rules that run in a constant inference tree. So here we look at the first tree. The first tree predicts residues from the base, and then the second tree targets errors from tree one. It's like a refiner. Then the third tree polishes the errors it got from the second tree. Then that one polishes. Then we had over 600 trees, and the last tree had 600 tiny corrections in total. It also uses a sigmoid curve, a sigmoid function, which is stated here. Basically, this was our best module that we used. It was the production model because we'll look next further why we had to choose it. And here is the logistic. We also used a couple of models like logistic regression, and the logistic regression is a linear. It is basically a linear model, and it computes a linear combination of input features and are mapped through the sigmoid function. And then we have the weight, the bias, then the feature X. And then we also use the random forest. Random forest also uses decision trees. It uses n decision trees, and we had over 500 decision trees. This is the function we used, and what it does is that it samples and averages their probability outputs. Then we have the cut boost. Basically, the cut boost handles it's like categorizing or ordering the data. So it was meant to do order boosting for the circle heterogeneity. Then we had the light GBM. Basically, the light GBM adopts a leaf-wise or best first growth strategy that focuses on computational effort on the leaf with the highest loss reduction, and it enables deeper and more accurate more trees with lower memory usage. Then we also have the EBM. The EBM is like a glass box. Okay, basically it does a glass box for regulatory compliance. What I will say about this glass box, it's like okay, it just evaluates using a glass box. Basically, we'll go to the tabnet. The tabnet, this one uses the tabnet uses a sequential sparse attention, as you can see the sparse function, and it applies this sparse mask to select relevant features per borrower. So this tabnet, after applying the feature subsets at each step, it continues with an attention mask, which is generated from the prior steps features using a shared fully connected layer with a sparse mask, and it forces the near zero values to exactly zero, and the mask is applied element-wise to the feature vector. Then you also have the tab transformer. The tab transformer, it maps it maps categories to dense embeddings or contextually updates via attention layers. This tab transform, what it does, it maps its categorical level to a dense embedding vector land, which is end to end. And these embeddings are passed through the multi-heads of attention layers, where each categorical variable conceptually updates its representation by attending to all the categorical variables in the same record. These were the findings that we had. You can see the regression had 0.4 and its accuracy was 0.62. 0.662. Then you can see when you go to the XGBoost, it had a 0.14, then the accuracy was 0.45, the precision was 0.2, the recall was 0.9, F1 was 0.4, then the F2 was 0.6, the OC was 0.64, then the area under precision recall curve was 0.32. And these were the results for everything. These are also the results from the production, which was under the precision recall curve. And then we chose XGBoost for production because of its stability mean test. In the F2, it had 0.76 and to almost 0.061 across all the 6 group split reshuffles, which had seeds from 100 to 105. It also had a single fixed split test F2, which was 0.61, which reflects a challenging partition of 30.14% test default rate, and that is the shadow mode deployment that is recommended. TabNet had 0.68 and Tab Transformer had 0.703, and it's not rank eligible according to the model. According to the models that we used. These are the explainable AI results that we got from discussion. I'll explain. This was one of the, okay, it basically showed why there are high risk loans rejected, and then this one showed that why were there more loan risk loans accepted. I'll go straight into the model compression. Basically, model compression was to bridge the gap between the gap that was between between the loans. Like basically, I'll explain how the rationale for choosing this knowledge distillation. As you can see, we had the extract, the transform, and the distill. So what happens is that in the project, we choose a primary objective, which is to deploy a highly robust credit intelligence across diverse circles. And then we also choose a teacher model, which is a heavyweight XGBoost model comprising of 600 trees. So here in the extract, we have we reveal the hidden relationships between classes by smoothing the teacher's confidence. Then we transform to the stripping of the sigmoid compression to retrieve the teacher's real decision conviction. And then in the distill, it creates the expert advice, and it targets that the student model is trained to mimic. So that we also had a distillation pipeline. This distillation pipeline is followed by a structured five-stage pipeline, as you can see, and it ensures that the student captured all the risk profiles of the Uganda lending data, and it was rigorously engineered to prevent data leakage and ensure that it applies to evaluation across all models. So the first is the data loading and identical preprocessing, where we eliminate the data leakage and we extract all the circle-aware group shuffle split generated in the main training phase that was reused. Then in the second, we establish the teacher's baseline. Here in the teacher's baseline, we use the context of the knowledge distillation, which acts as the baseline and acts as the teacher's report card. Here, the teacher may be, okay, what I can say, like the teacher represents the gold standard or the score to beat, and then the XGBoost teacher established a baseline of rock oak of 0.671, and then we go to generating soft labels. Generating soft labels is like training a data set that was passed through the fitted teacher to extract probability distributions rather than the binary 0, 1 inputs. And then we go to the loss blending. As you can see, the function that we use, the loss blending is just to train on a weighted target. Then lastly, we go to the student training evaluation and selection, where we use three distinct student architectures which can be trained, and we evaluate against the hard truth baseline and against the teacher baseline, and then we compare against each other from which the best student was selected. And here we use the linear regression. Let me show you the results. We used linear regression. We used XGBoost. We used logistic regression, and it was a single decision tree. Then we used a small gradient boosting, and we trained all these, and we predicted that these two targets instead of the raw Boolean targets. And these were the results. So when we distilled against that distilled baseline per student, we saw that logistic regression had 0.003. As you can see the results, then decision tree had 0.2, then gradient boosting was small and it was 0.1. This was negative, this was 1, but this was 0.2. So in summary, we saw that the single decision tree student had achieved significant performance gains over the 600 tree XGBoost baseline. And the performance was that in knowledge distillation, there was regularization, and the label smoothing effect was T to 2. And it means that the student was 0.745, which versus the teacher who had scored 0.671. In summary, we chose the model completion, the model as XGBoost because of its best circle stability across all the tests, and then it confirmed the clean causal features, and we also had a 7 leakage audit. This is the deployment phase we had. Phase 1, we had the shadow mode where you run parallel with manual process. Phase 2, we had assisted decisioning, where we had high-risk applicants routed to senior officers. Then phase 3, we had political integration. In summary, we also had to deploy, this is the URL for our API, where you put your credentials and then the API scores your details, and then you get a result of, if it is above 50, yeah, it means you'll have high risk of high percentage of defaulting, and then when it is below it, you have a low percentage rate of defaulting. Some of the limitations we had, but we had less data. We had less data for module 2 because there are some features that don't work with module 2, and it was designed and architected in this study. Light GBM, which is a 3-class classifier, also deferred to a companion publication, and it didn't help us in evaluating module 2 properly. Then we also had the geographic institutional focus, because this model performance may vary when applied to microfinance institutions in different geographic areas or economic jurisdictions where lending behavior and regulatory frameworks differ substantially. We also had a class imbalance of 3.1 to 1 ratio, and despite this ensemble imbalancing, there is minority class pass-through, which remains a challenge and potentially leading to conservative scoring volatile edge cases. In conclusion, we had to conduct the model architectures. We had to model architectures. Then we had to also perform the 24 question EDA. We also had to to get a 7-step leakage, and also designed a trusted MVP suitable for shadow mode pilot deployment. The feature works. We suggested that we have a phase 2 data collection and get as more records as possible, like linked savings and days to disperse. Then we also have to get federated learning to teach people, and then we also get the formal fairness audit. Then we also get an ASD mobile interface to help loan officers in areas with limited internet connectivity, and also get a deep model stability to help us with coordinating with full tabnet and tab transformer stability analysis in expansion. Um, I acknowledge these are the references that we have. Yes, and then I acknowledge our supervisor, Dr. Galiwango Marvin, and Dr. Efrens Eunice Namugenyi, Macquarie University from College of Computing and Information Sciences, and our partners for the over 50 Ugandan circles who trusted us with their data, and the community, the Uganda Microfinance Regulatory Authority, which served as our community with Bank of Uganda and East African FinTech Community. Thank you so much for listening. I remain Nachamba de Mariam.